Good morning. Thank you very much for coming for my presentation lecture. So today I would like to speak about CO2 assisted dehydrogenation of propane to propane or Zn-BEA zeolites and impact of acid-base characteristic on catalytic performance. This is This is work obtained by collaboration with Institute of Physical Chemistry. I am from Sorbonne Universite in Paris, in collaboration with Svetlana Orlik, Pavlo Kirienko, Andrei Kapran, Yannick Milo, and Stanislaw Dzwigaj, my name. Okay, then I would like to speak you about context of this work. Transition metal introduced in the zeolite flower as isolated species is very interesting from the point of view of catalytic processes. So, a zeolite catalyst with isolated center is difficult to prepare because of the speciation problem related to the starting components, the solid and the metal precursor. Different species can be formed in the zeolite, which we use metal oligomers, metal oxide nanoparticles, isolated flower, and extra flower metal species. So where can transition metal species can be formed in the zeolite? So there are several positions. Specific position as isolated extra flower species, isolated flower, and extra flower metal oxide. For us, more interesting is incorporation in the flower position. Is very difficult because we should look for the special method how to incorporate metal in this position. So I found several years ago method to preparation such an incorporation of metal in the flower position to reach this objective. Two-step post-synthesis method can be used by controlling pH and concentration of precursor. Advantage of such preparation is to restrict the speciation of transition metal in the catalyst to the single mononuclear transition metal sites. So now I would like to show you how we can introduce, for example, vanadium. So vanadium is used very often in the different test reaction. To obtain vanadium beta zeolite, it's important to creation of vacancy site by removal of aluminum and by treatment with acid nitric. In this case, we form vacancy site and then we contact ammonium metavanadate solution with the zeolite, and the reaction between vanadium precursor take place with OH group, and vanadium can be incorporated in the zeolite flower. But it's easy to show, but it's important to confirm that this is like that. So for this, it's important to look region of predominance of vanadium species in the case of ammonium metavanadate. So as you can see in the function of pH and concentration, we have in the solution different kinds of vanadium species. This is a mononuclear vanadium species, but in this case, this mononuclear also, but with polynuclear. So there is several possibility. For us, this is not interesting because in this case, we have different kinds of vanadium species, in particular polynuclear vanadium species, which can be difficult to incorporate in the flower position of the zeolite. So we work in the condition of pH 2.5. In this condition, as you can see, we have mononuclear vanadium species in the solution. This is not very big molecules. Molecules could be incorporated in the vacancy site. So here we confirm by infrared spectroscopy that we remove aluminum from Al beta zeolite. Aluminum is in this position. When we treat it with nitric acid, we remove aluminum and we create vacantity site. So how to prove this? We observe infrared spectroscopy, and in infrared spectroscopy for Ac beta zeolite, for Al beta zeolite, we have particular band. This band is characteristic for the presence of aluminum OH group. And what happens when you remove aluminum? So we create this, and it's very easy to write this, but it's more difficult to confirm. So this is the formation of this OH group, hydrogen bonded OH groups, is confirmed by infrared spectroscopy with formation of the band, large band at 300, 520. And also isolated species like SCOH. Then when we contact VO2 plus, here, the VO2 plus, we contact with this Sc beta. What happened? VO2 plus react with OH group, is incorporated in the parameter position with formation vanadium beta zeolite. So here you have vanadium Sc beta. What happened in the infrared? In the infrared, we observe decreasing, disappearing of this band. What means that this group interact with this and with formation of this, and this is disappearing. And now, with another technique, we can confirm that really this is happening. Why? In the first, by NMR, vanadium mass NMR, we can see that when we have ammonium metabolite solution in pH 2.5, we have particular species in the C by mass NMR, and this species is when we contact ammonium metabolite precursor with Sc beta, what happens in the solution? This VO2 plus is disappeared, and with disappeared. So you can observe this by NMR, and then with formation new band. This band is here. This is band characteristic for vanadium tetrahedral vanadium species. Wow. Okay, so this confirms that reaction between precursor and Sc beta take place with formation vanadium tetrahedral species. Then we also look for another phenomena. What happened when the content of the vanadium is increased? So we observe in the beginning for the low loading vanadium tetrahedral vanadium species for low loading, but with an increase of the content of vanadium, what happened? We observe also vanadium octahedral species. This band is characteristic for vanadium octahedral species. So this is confirmed also by UV visible that that formation in the beginning there is formation only tetrahedral vanadium species like that, and this band is characteristic for this, and this band is characteristic for this. So when we increase the vanadium content, we in the UV visible appeared new band very large band with characteristic for the octahedral banana species present in the extra Fraunhofer position. And then what happened when we change pH? So we were before in pH 2.5. Now we change pH of the solution to 6. What happened? So in this condition, in this concentration, we have not only mononuclear banana species, but also polynuclear banana species. What happened in the zeolite? In the zeolite, we form tetrahedral banana species like that with VOH group, this group. And in contrast, in pH 6, this bond is not very clean. So because we form not only Fraunhofer vanadium species, but also extra Fraunhofer vanadium species. This is confirmed by UV visible, as you can see. In this case, with increase in pH 2.5, we have only tetrahedral banana species. In pH 6, we have tetrahedral banana species, but also octahedral banana species. So now we can see that when by second mass NMR, what happened? When we have a small, when we have AC beta IC, so we have the band characteristic for the presence of OH, SC or OSC free species, this one. When we incorporate vanadium, what happens? This band disappeared because consumption of this group by vanadium. This is completely consumed situation, but when we were in pH 6, the situation is not the same, because in this case, we have only partial decreasing of this band. It means that only partial formation of vanadium tetrahedral species in the Fraunhofer is appeared. So in party of the vanadium is going out in the extra Fraunhofer position. So the situation in pH 6 is not good, like in the case of pH 2.5, where we have only tetrahedral vanadium species formed. Now, because we use this catalyst for oxidative dehydrogenation of propane, so now I would like to show you by EPR spectroscopy situation in this zeolite when we calcine this zeolite. So we have only, we haven't EPR signal because vanadium is in 5 as vanadium 5. So when after ODH test, what happened? There is a reduction of vanadium 5 to vanadium 4. So in this situation, a vanadium 4 signal appeared in EPR spectroscopy. And by simulation, we can calculate number of tetrahedral vanadium 4 species and octahedral vanadium 4 species. And as we can see, by calculation, we can obtain a ratio tetrahedral to octahedral up to 10. That means that practically in this condition we have tetrahedral vanadium species. So this is in pH 2.5. The situation is very good. Vanadium is incorporated in the Fraunhofer as isolated species. Then, in contrast, it's not good. Yes. Also, in the case of preparation at pH 6, as prepared catalyst, we have vanadium 5. We haven't vanadium 5 signal because EPR spectroscopy give out only vanadium 4 signal. So when by ODH test, the vanadium 5 is reduced to vanadium 4. And in this case, we have EPA signal. And by simulation, we can calculate also ratio tetrahedral to octahedral species. So we can see that the ratio is only 0.5. That means that there is tetrahedral and octahedral species in the zeolite in this case. So we use this catalyst for oxidative dehydrogenation of propane reaction, and so we can. So here we have the results of this reaction. So this is, we can see that at in the case of vanadium Ac beta zeolite prepared and pH 2.5, so the propane rate formation is 10 times higher than in the case of preparation pH 6. Also, turnover frequency show us that turnover frequency is 10 times higher than in the case of preparation pH 6. So it means that in the case, in this case, we have only tetrahedral vanadium species in the zeolite. Here, in this case, we have tetrahedral and octahedral vanadium species. So, because the rate of propane formation is 10 times higher than in this condition, so that means that tetrahedral vanadium species which is present in this catalyst, some responsible for the oxidative dehydrogenation of propane to propylene. This is the active site of this reaction. So, in conclusion, so we can see that at pH 2.5, the predominant mononuclear vanadium plus ion reacted with the SeOH group created by the desalumination, and this led to the formation of pseudotetrahedral vanadium species. In contrast, in the pH 6, mononuclear and polynuclear vanadium species coexist in the impregnated solution, and both Fraunhofer and extra Fraunhofer vanadium species can be formed. This is indicated and confirmed by UV ZIPS measurements and mass NMR. So in this case, turnover frequency of propane oxidative dehydrogenation of oxidative dehydrogenation exhibiting that Fraunhofer vanadium species one order of magnitude higher than those of in the case of zeolite with extra Fraunhofer vanadium species. So this suggests us that isolated pseudotetrahedral Fraunhofer vanadium species would be the active sites of propane oxidative dehydrogenation catalytic process. So this I show you that we think that this pseudotetrahedral vanadium species is active sites of propane to propylene oxidative dehydrogenation, and not polynuclear vanadium species. So now I would like to show you another application with zinc prepared by similar two-step post-synthesis method. And in this case, we create also vacantity site by nitric acid treatment with removal of aluminum in the first step. In the second step, we contact zinc precursor with OH group with Ac beta. So in this case, you see that in this case we have Ac12 up to 1,500. It means that in this zeolite there is no aluminum. So here we form zinc beta zeolite, and for example, we prepared Zn beta zeolite with 1 weight percentage, and then we use this catalyst for dehydrogenation of propane to propane with using CO2 as mild oxidant. So why such application? Because among of the on-purpose technology for propellant production, the catalytic propane dehydrogenation with CO2 is of particular interest, as you know, because of the problem with CO2 as a greenhouse gas on the industrial scale. So we use this because of this. Then we prepared 3 kinds of catalysts. This means catalyst with 1% of zinc and Al-beta zeolite, Sc-beta and Sc-beta zeolite. Introduce zinc on this support. So we form Zn Al-beta, Zn Al Sc-beta is Zn Sc-beta. What means that in this case we have a ratio SeOl 17. In this case, ratio SeOl is 100. In this case, the ratio SeOl is 1000. So after we use, we characterize this catalyst by several techniques, physicochemical technique, to know what happened, or is the acidity of this zeolite, what is the microporous and mesoporous volume, etc. So the reaction is going in this condition. So now I would like to show you that structure and textural characteristic of zeolite Zn beta sample. So we can see that XRD diffraction of these 3 catalysts is very similar. This means that during desalumination and incorporation of Zn, there is no affect, does not affect of the crystallinity of the zeolite. Also, by different technique, we can see that microporous and mesoporous are present in these 3 catalysts, but desalumination is going to formation more extra more mesoporous pore. So this means that full deamination caused by formation of mesopores with the larger diameter surface and specific surface area. So by silicon mass NMR, we can see that in this sample there is characteristic band peak related with the presence of silicon in different environment. Now the acid-base characteristic of the zeolite have been done by ammonia TPD and TPD and CO2 TPD. Ammonium TPD is here, and CO2 TPD is here. So we can see that in the case of this catalyst, there is this several kinds of acid sites, and contrast, there is also basic sites present in all these catalysts, but with very small amounts of basic sites in the case of Zn-Sc-beta zeolite. As we can see, total basicity is here. So in the case of Zn-Sc-beta, there is 2 times less than in the case of these 2 catalysts. In contrast, total acidity is also the smaller in the case of this, but we can distinguish different kinds of acid sites, weak, medium, and strong. So in the case of Zn-SC-beta, by desamination, we remove aluminum. So in this case, strong acid site is very small amount in these two cases. So full delamination of beta followed by introduction of Zn into vacantity site of the zeolite result in reduction of the total acidity and reduction of the total basicity. So now nature of the acid sites on the surface of Zn beta was shown by infrared spectroscopy with adsorption of pyridine. So we can see that in the case of Zn beta, we observe Lewis and bronze acid sites. In this case, also Lewis bronze acid site, because this bronze acid site is related with the presence of aluminum. In contrast, in the case of Zn-SC-beta zeolite, we remove aluminum, so we don't observe bronze acid sites in this case by infrared spectroscopy. But we have Lewis acid sites in the case of Zn-SC-beta. Okay. Now I can show you very quickly the propane dehydrogenation process and result obtained in this case. So we can see that at 8 in this temperature, the selectivity in the case of Zn-SC-beta is up to 94%, is much higher than in the case of this catalyst. So it means that this catalyst with Zn in the primary position is a better catalyst for propane dehydrogenation into propylene. Okay, so now I can show also that the effect of the presence of CO2 here. So the result obtained with CO2 is more important. You can see that in the presence with CO2, propane conversion is much higher than without CO2. This is a very interesting point of view. And we also observed deactivation and carbonization of Zn-beta zeolite in the case of Zn-beta zeolite. In contrast, in the case of, so we can see here that in the case of Zn-SC-beta, this formation of carbon is very small. So it means that in the case of zeolite prepared with incorporation of Zn-SC-beta, Zn in the SC-beta zeolite allow to obtain very good catalyst without formation of carbon. So now we can show that what happened when we do desalination. Full desalination, as we see here, full desalination leads to bronze acid site elimination. So in the result of dehydrogenation of propane with CO2, so we can see that selectivity to propylene is very important. It's 90%. In contrast, in the case of these two catalysts with aluminum, there is not a good catalyst, because for us more interesting is to formation of propylene. So we can tell that in conclusion, that post-synthesis procedure of preparing 1% of Zn-beta zeolite, including preliminary, partial, and full delamination of the dental beta zeolite, Initiate specimen SeAl17, followed by introduction Zn cation into vacancy site of the zeolite, leads to reduction of the total acidity and compared to the total acidity, reduction of total acidity, and reduction of the total basicity. Food elimination also results in development of the mesopore structure and specific surface area of Zn SE-beta compared to Zn Al-beta, creating acid sites related with the presence of Zn2+ and basic site oxygen and oxygen vacancy of prominently medium strength and removing Bronsted acid site from the surface. So, in the presence of Zn SE-beta catalyst, the achieved selectivity for propylene is very important. It would yield 30% related to the propylene in the CO2 propane dehydrogenation process. This exceeds this for obtaining for Zn Al-beta is Zn Al SE-beta. So the positive effect of the food elimination on selectivity and lower deactivation with increasing turnover frequency is mainly attributed to the lack of the basic sites on the surface of Zn SE-beta, which are capable to protoning the production of olefin and thus intensify the site reaction of oligomerization and cracking with the subsequent coating of the catalyst surface. It's not good. It means that the coating is not good for this reaction. So we should work with delaminated catalyst, which is selective for this propane formation. So a comparison of the achieved selectivity and yield for propylene in the dehydrogenation of propane without carbon dioxide demonstrate the advantages of the propylene production in the presence of CO2 using Zn-beta zeolite. It's very important for the point of view application of CO2 and removal of CO2 from the environment. So thank you very much for your kind attention.